Okay, in this next example, this is a very popular type example. So it's a rate problem. It's a distance and a rate and a time problem. And so the way I like to solve distance, rate, time problems is by organizing the information into a table. Before you even start with your table, do we understand the relationship between a distance, a rate, and a time? Let's say that you're driving down the interstate and you're going 75 miles per hour. So that's your rate. This is a quick side note here. I'll do it at the top since I have space. Side note. So suppose you're driving somewhere and you're going at a speed of 75 miles per hour. I'm going to write that as miles per 1 hour. Okay. That's what your speed is registered at, 75 miles per hour. And you maintain this speed, this constant speed for 2 hours. So your time is 2 hours. And we want to figure out the total distance that we've driven. So without telling you that this is a math problem, you know what to do. Well, if I drive 75 miles per hour and I do this for 2 hours, the distance I have traveled is 150 miles, right? That's pretty clear. It's pretty obvious. We've all driven places before or been passengers of somebody who's driven us places before. We understand this. So now as an equation, now let's take this and put it into a math problem. The distance that you achieved, 150, you could have gotten by multiplying 75 times 2, right? 75 times 2. In other words, your distance is equal to your rate times your time. And that is the math formula that we need to know whenever we're working with problems that involve distance, rate, and time. Distance equals rate times time. Okay, so I'm going to organize this into a table. I'm going to have 3 columns, maybe even 4. 4 columns, let's say. I need a column for D, R, and T. I also need a column for which direction my movement takes place. Okay, so you're going to have 2 separate equations for this distance equals rate times time. One equation is going to be for the downstream direction, and the other equation is going to be, oh, you know what? I just lied. No, upstream. Okay, that was right. So I have an equation for going downstream, and then I have an equation for going upstream. So those are your 2 separate scenarios, downstream and then upstream. Okay. Let's begin our setup here, our little table or our spreadsheet kind of thing. So we've got downstream. And we've got upstream. Okay. We've got a rate. We've got a time. We've got a distance. Okay, so what do we know? Now that we've got our blank table set up, we have to start filling in with the information that we're given. Distance equals rate times time, okay? What do we know? Pamela requires 3 hours time to swim 15 miles downstream, okay? 3 hours time, so we're moving downstream. Look at that top line. For moving downstream, she requires 3 hours to do this. And she's traveling a distance of 15 miles, okay? Now let's move to upstream. She's going to turn around. She's going to go back upstream. Now upstream means she's swimming against the current, right? Upstream against the current. Let's write that out. Upstream against the current. Downstream with the current. Downstream. Okay, so we've got that understood. Now, she's swimming upstream. It takes her 5 hours to swim upstream. That's all it says. What's the distance that's needed to swim upstream? So if the distance to swim downstream was 15 miles, and she turns around and she goes back to her exact same place where she left, that's the same distance. So that's an assumption we needed to make that might not have been obvious until we talked about it. Now let's talk about the rates. There's actually two rates, and I know this because the problem says find her average speed in still water, and then how fast is the current. Those are the two components I have to figure out. I need her average speed in still water, so that's without any current whatsoever. And then I need her, I need the current speed. How fast is the current? So we'll say that's current speed. How fast is that river flowing? Okay. So her speed in still water I've represented by X, and the current I've represented by Y. Now think about swimming upstream. Okay. So think about swimming upstream. That's the red highlighted, or the red underlined piece. When you're swimming upstream, that means you're against the current, okay? If you're swimming against the current, are you going to be traveling faster or slower than you would have in still water? If you're swimming against the current. If you're swimming against the current, your speed is going to slow down because the current is pushing you backwards, okay? Her speed in still water doesn't change. She's not working any harder to compensate for that current speed. She still has her own personal rate that she can swim, and she's not changing that at all. And so if she's swimming upstream against the current, she's moving slower. The current is causing her to move slower. And if you're swimming downstream, that means the current is making you go faster. Okay? You're going faster if you're swimming with the current. The current is helping you. Whereas against the current, when you're going upstream, the current is hindering you from going as quickly. So when you come up to your table and figure out the rate that you're traveling downstream, you take the swimmer's individual rate, whatever she can do in still water, and then if you're going downstream, your overall rate is going to be even faster, because that current speed is making you go that much faster. Now going upstream, the opposite is happening. You've got your individual swim capacity rate, and then you're going to be slowed down by the current. So you're going to be subtracting that current speed. Now that helps you, your table is completely filled in. We are going to now come up with our system of equations with 2 equations and 2 unknowns. All right, so here we go. One equation is going to be working with the downstream line. We know that the rate, x plus y, and put this in parentheses for me, right there in the table so we don't forget. The rate going downstream times the time to go downstream equals 15. And then the other line, upstream, that rate, times the time to go upstream, it should take longer, right, because you're going slower, is also equal to 15 miles. And that's your initial system. And we are going to simplify this just a little bit. I'm going to write that as 3x plus 3y equals 15, and 5x minus 5y equals 15, right? It's distributed those constants. All right, so now I've got this system of equations. I can solve for x and y using any method that you like. They are both equal to 15, but it would not help you to set them equal to each other because then you're still going to have an equation with 2 variables in it. So I don't recommend you do that. Instead, I would suggest that you could, let's go ahead and use our substitution method again. So I'm going to take that top equation, which is 3x plus 3y equals 15. And I'm going to divide everything by 3 because that is a common factor. So x plus y equals 5. And let's solve it for y this time. Y is equal to 5 minus x. For the substitution technique, you're going to take the 5 minus x, you're going to substitute it into the opposite equation. So what did I work with? The top one. I'm going to substitute this into the bottom equation now for the variable y, and that's going to look like 5x minus 5 times the parentheses of 5 minus x equals 15. So now you're going to solve this however you would like for x. Yes, you could divide everything through by a 5. Not everybody's going to see that that's possible, so I'm not going to do that. Instead, I'm going to distribute this 5 and call it minus 25 plus 5x equals 15. And combine your like terms, 10x. Get the 25 to the other side, that's 40. X equals 4. We are in miles per hour, hour units. X stands for the average speed in still water. This individual can swim at the rate of 4 miles per hour in still water. It's a pretty good clip. Okay, now we're going to find the current's speed, the current of the river or the stream or wherever we are. The current speed is found by plugging 4 for x into n of our equations that involve x and y. I like this one because it's already got y by itself. So y is equal to 5 minus the value I just calculated for x, and that's 1. So the current speed is 1 mile per hour. Okay, double check your numbers to see that they make sense. It wouldn't make any sense for this individual to be swimming at like 40 miles per hour. That is physically impossible. Or the current speed to be like 100 miles per hour. That would be horrible. So double check your answers just to make sure that they make logical sense. And that should take us to the end of 10.1.